harmonic motion, I gave you yesterday two sort of ways to define it, right? Two ways to understand it. The second way was the sort of more technical way, but it's a little hard to understand if you just get the equation on its own. But I want to come back to it. Okay? So the subheading you can make is differential equations. Right? And I said differential equations plural because you've actually met one of these before in the last topic we did. Okay, so do you remember? We start out saying particular situations, right? The natural growth and decay. They follow this particular differential equation. I just didn't call it that. Things like this: dp on dt, okay, is equal to kp, right? Or minus kp, right? Now, what is this? Again, there's your first derivative. Bless you. Okay, and there's your original function. And the relationship between them is that they're proportional to each other. Okay. Now, the way we thought about this was, what kind of function, what kind of family of functions fits this kind of description? When you take a function and you differentiate it, essentially you get the same thing back. The only difference is the scale, or the constant out the front. Okay? And we said, okay, we know exactly what this looks like. This is an exponential function, right? Things like this. Okay? And when you differentiate, chain rule brings that k out the front, and there's your differential equation. Okay? So therefore, when we're thinking about this is the equation I gave you yesterday. X double dot is equal to minus m squared x. Okay? Can you see the parallels between them? Okay, instead of p's, we've got x's here because that's our customary way to indicate displacement. But really, same deal, right? Second derivative there. Another constant out the front, and there's your original function. Excuse me. Now, in just the same way we looked at before, right? We said, what kind of function do we know that behaves like this? When you differentiate it, you get the same thing back, okay? So the question is, wait, sorry, that shouldn't be a D. That's just an X. What kind of function, if we differentiate it twice, gives us back basically the same kind of function? And the answer is a trig function. We've seen this before, right? So I'm going to give us this kind of definition, a simple one to begin with, and then we'll expand on different simple harmonic motion, different variations on it later on, of sine or cosine, it doesn't matter, of nt. Nt. Now, let's have a look at this for a second. When you differentiate this, differentiate it once and you'll get velocity. Okay? So velocity, when you differentiate with respect to time, this is just simple chain rule, right? So on the inside here, I've got nt, so I differentiate, I get n. And on the outside, I've got sine, so it turns into cosine. Okay. Now there's velocity. To get my acceleration, what I get from here, right, I've got to differentiate again. So acceleration, or force, right, there's another instance of chain rule. So the n comes out the front again. Okay, so I've got two lots of n. But of course, cosine doesn't go back to sine, it goes to negative sine, right? And now you can see where that minus n squared comes from, yeah? So I'll just bring that. All right, so that's why we're going to use these basic trig functions as the basis for how we're going to discuss simple harmonic motion. Later on we'll introduce, okay, what if instead of just sine of nt, which is very, very simple, it means you start off at the origin because you substitute t equals 0 in there, and you'll get x equals 0. We're going to look at different kinds of shift. So x equals sine of nt plus alpha, and also different kinds of amplitude, right? So things like, say, a plus sine. I should have put it at the end. Plus a, so that's going to change your equilibrium position, your center of motion. Okay, it'll move you up or down, and of course we can also change the amplitude if we like. So let's stick an R out the front there. Okay. So these kinds of different versions of this, they all work the same way. They still follow these results because when you differentiate, you're still going to get essentially the same thing, though this constant will just be a little different because it disappears each time.